In this next video, we're continuing with section 3.3, and now let's start talking about the second derivative. Again, if you're following along in the book takes this first derivative information a little bit further, and I'll come back to that in a moment. I'd like to move into the second derivative. And I'm going to spill the beans a little bit. The second derivative tells us about the concavity of a function. So I'm just going to establish two questions up here. We're going to ask, where is our function concave up? And secondly, where is our function concave down? But before I can establish that, and before we can fully answer that, let's take a little moment to talk a little bit more about concavity. So I'm sticking with my first page here. When you get my note package, this is going to have a lot of the overall summary. So I still have that first theorem. We will get a second theorem to go along with this idea in a moment. But first, let me just come to the bottom of the page and let's talk about concavity. We've already established the idea of increasing, decreasing, and that all that tells us, I should say, is just about whether the function, the shape of the curve, is going up or going down. So this would be an increasing portion of a graph, but so would this. They each are increasing, but they have a different concavity. And similarly, if I was decreasing, this is decreasing, but so is this. Both of these are decreasing, but again, different concavity. The concavity really talks about the literal curvature, which way the graph curves. And in this general description, concave up is like this upward-facing parabola. That is a big picture version of concave up. And then concave down, this upside-down parabola, this would give us the full picture of concave down. So just looking at those, the idea of concave up, well, it has this big U, so that consists of a portion where the graph is decreasing and is also increasing. And similarly, when we look at concave down in the big picture, we've got a region where we're going up, increasing, and a second region where we're going down, decreasing. So while that is the big picture, any of these half curves would also count. So if I just had this piece, I'm only looking at half of the U, but that would still be concave down. This increasing would be half of this U, and that would be concave up. Similarly over here, this would be half of this U, so this would just be decreasing and concave down. This would be decreasing and would be half of this U, so that would be decreasing and concave up. I'll come back to the second derivative in just a moment, but now just having that basic idea, we'll come back to the top using this original graph that we had for f and come back to these two questions. So where is the graph concave up? Well, still, start on the far left side. As soon as I get on my graph, that's x is negative infinity, and the first thing we see is this nice concave up shape. It's not as easy to say where you change concavity, but we could still do a decent job approximating it from the graph. So just looking at this, I see the concave up, but what happens when I keep going? Look right here. This is subtle, but that's a part of an upside down U, and that's concave down. So I would say it's right here. That's a coincidence it happens to be an x-intercept, but I would say right about here at x is -2 is where we make the transition. So concave up right here, that would be negative infinity. And again, we're approximating to about -2. And then I get a small piece of concave down. And then notice, then I get a small piece of concave up. This is half a U. This would be the other half that's not here, just as this was half of an upside down U, with the other half would be right here, but is not there. So I'm getting a small piece of concave down from -2 to -1. And then I get concave up from -1 until that peak at +1. And now I get a whole big section of concave up again. And where does that stop? Again, there's a little shift here at the end. Notice this little piece here, that is definitely not an upward U shape. It's more of that flattening off, starting to make that upside down U. So I'm getting concave up here. That would be 1 to 4. And then I get concave down for the end, 4 to infinity. I intentionally chose a little bit of a tough one to try and demonstrate this, everybody. It wasn't the easiest thing to see, but we get to start to establish the ideas of both concave up and concave down. And not as easy as increasing, decreasing, but if we're lucky enough to have the graph, that can basically be established just by looking and understanding what it is that we're looking for. But when we have equations, we're going to need a theorem similar to this theorem. I've kind of already spilled the beans. The first derivative tells us about the original function and its increasing, decreasing. We're going to get a similar two-part theorem that tells us about the original function being concave up. For short, I'll start abbreviating that CU for concave up, and we'll have the original function being concave down for the second part. And I'll use CD for concave down. These will also be if and only if statements. And we're going to see this answer from the second derivative. Again, we're still having if and only ifs. We'll still see how we can use this back and forth a little bit. But first thing, what is the result that we need? And let's come back down to this for one more moment. I'm telling you that it's connected to the second derivative, so let's think about these at their most basic graphs. This, an upright facing parabola, would be y equals x squared. What happens to its second derivative? Well, its first derivative is 2x. Its second derivative is positive 2. Look what happens over here. This is an upside down parabola. Its most basic equation would be negative x squared. So its first derivative would be negative 2x, and its second derivative would be negative 2. So what are we supposed to get from this? Well, it's just an example, but it's demonstrating what we're going to get for the rest of this theorem. The original function is concave up if and only if the second derivative is positive, if the second derivative is greater than 0. And that the original function is concave down if and only if the second derivative is less than 0. So that pretty much gets all of our facts, but let's get some more problems. We'll see these concavity problems when we're dealing with equations are going to be very similar to the increasing, decreasing problems that we had a moment ago. It's just that we'll use the second derivative. So let's get a problem. We'll do a couple of these. Again, this is very similar to the increasing, decreasing, just that you're using the second derivative. So where is the function concave up, and where is the function concave down? And let's start off with number 1. Let's use the function e of x is 1/4 x to the 4th plus 2x cubed minus 2x plus 7. And starting with, I'm not going to say easy, but a little bit of an easier first problem. Want to know about concave up, concave down? The key is not to try and sketch the graph of this. The key is to use the derivatives. So now from the previous theorem, we're establishing it's the second derivative that connects us back to the original function concave up, concave down. Go back to what I said about this first theorem. You can't use it. There's too many variations of the function to just say it. You can't say it increases when it is positive, it is concave up when it is positive. You got to be more clear than that. Original increasing when the derivative is greater than 0, positive. Original function decreasing if and only if the first derivative is less than 0, negative. Original function concave up, if and only if second derivative is greater than 0, second derivative positive. Original function concave down, if and only if second derivative is less than 0, second derivative is negative. That's what you need to establish. So, coming over here, let's do that. Well, first things first, I need the second derivative. So let me start with the first derivative, nothing fancy, simple addition, subtraction. So just taking derivative, basic power rule, 4 times 1/4 cancels, so I get an x cubed plus 6x squared minus 2. And now I move right into the second derivative. 3x squared plus 12x. Again, simple addition, subtraction, so simple derivative. I will set this equal to 0. I will also consider where it is undefined. They're not critical values. That word critical values is specifically used when you're looking at the first derivative equal to 0. But they serve a similar purpose here. There's no formal name for these. We'll just call them the important spots. Where are the important spots in the second derivative? They're where the second derivative is 0 or undefined. Just like we were seeing with the first derivative equaling 0 and being undefined, there's no denominator, so I don't have to worry about the undefined portion. But just setting it equal to 0, well, still have to factor a little bit. 3x times x plus 4. So I'll get two important x values. 3x equals 0 gives me 0, and x plus 4 equals 0 gives me negative 4. Excuse me. I'm still going to make a test interval. All this tells me is where the second derivative is equal to 0. So I'll make a test interval, putting those important x's in order. And for my own notes, realizing that this is the second derivative test interval, I'm going to do the same thing I was doing. Pick an x for each interval, plug it into the factored version of the derivative to check your signs. So I'll use x as -5 over here. -15, -1, negative gives me a positive. Don't even worry about the numbers, everybody. 3 times -5 is -15, but again, you really just need the sign, negative. -5 plus 4 is -1, still just need the sign negative. And a negative times a negative is the positive. Then I'll use x as -1, I'll get negative positive, so that's a negative. And I'll use x as +1, I'll get positive for a positive. All these test intervals, again, the most common thing is that the sign changes from one interval to the next. But again, we have to test. We can't just do it on 1 or 2. We have to test all 3 to know for sure. And this one does have that, the sign changes for each interval. But now answering the question, so my e function is concave up, where the second derivative is positive, so I'll get 2 intervals. I'll get -infinity to -4 here, and then 0 to infinity here. E is concave down, where the second derivative is negative, so I'm only getting 1 interval here. That would be -4 to 0. So a nice first problem, and we'll get more practice with the second derivative, but for right now, let's just do one more. Let's look at number 2. Let's use function g of x, and g of x is equal to 4 over the quantity 3x minus 3. Still need to get to the second derivative. So first derivative, then second. Quotient rule is not that terrible here. I'm going to be a little crafty though, and just to realize I could bring that whole expression up as a -1 exponent. So I'm going to take my derivative using chain rule instead of quotient rule. I'm going to use this form. You'll notice if you use quotient rule, you'll get the same thing I'm going to get in a moment. It's just a slightly different technique. It's not a huge difference here. This isn't that bad one way or another. But I'm using chain rule. -1 makes that a -4. 3x minus 3 to the -2 power times an extra 3. I could clean that up. -12 over 3x minus 3 squared. But really, since I really want to get to the next derivative, that's really as far as I should go with my cleanup. And from here, second derivative, positive 24, 3x minus 3 to the negative 3 power times an extra 3 for the derivative on the inside. And this is the function I want to focus on. So as I was kind of mentioning a little cleanup here, this is really where we should use that cleanup. 3 times 24, we'll get a positive 72 over quantity 3x minus 3 cubed. Where does this equal 0? It doesn't. Numerator does not equal 0. We don't get any important x's here, but setting the denominator equal to 0, I just get one important x value. We get x equals 1. So that's it. Only value that needs to be marked off. Harder function, looked like more was going on, but only one critical value. So every one of these problems, I'm sorry, this is not a critical value, one important value. My apologies, one important value. Every single one of these, you can't say there will be one important x or 2 or 3 or 4. You really have to look at each problem separately and make sure we're looking at just what happens, not trying to make any grand conclusions from just doing 1 or 2 example problems. Okay, so now I've got that set up. Again, second derivative, I'm testing right here. I'll use x is 0, so I get a positive on top. 0 minus 3 is negative, a negative cubed is still negative. That gives me a negative. And then we'll use x equals 2 on the other side. Top is always positive. I would get 6 minus 3, positive, positive cubed, still positive. I get a positive. G would be concave up from 1 to infinity, this interval, and G would be concave down on this interval, negative infinity to 1. Again, everybody, the book, as you do some of your homework, they'll ask you these questions. Sometimes they'll give you a little information and ask you to sketch. Again, we'll get more practice in 3.5. It's worth trying now. It's worth to get a few little problems out of the way, but we'll really see a lot more in 3.5. So, good problems. But to realize everything I've been doing so far, these are all based off the equations, and everything so far has really been using this part of the theorems to tell us about the original function. And we could still do some more in that way. Let's look at problem number 5. I'm sorry, this is page 5. And let's look at something a little different. I want to give you the sketch of f prime, and I want to ask you questions about f. So this initially looks a little bit like the regular problem we started with, but we really have to establish the theorem. So I'm going to have nothing too crazy here. Let's just do this. So there's my function f prime, and I'm going to ask several questions here. Where is f increasing? Where is f decreasing? Number 3, where is f concave up? And number 4, where is f concave down? One of the big challenges in this section is that you really have to get used to using those theorems to get to whatever you can to answer what they're asking. So again, if this was f, where is this increasing, decreasing? That would be a piece of cake. It's going up, it's going down, it's going up, and you've answered those 2 questions. If this was f, where is it concave up, concave down? There's concave down, there's concave up, there's a little extra concave up right here, but it would still be very basic, and we can kind of jump and just answer by looking. But the issue is this is f prime. So where is f increasing? Again, we have to retranslate the problem. Knowing about f prime, but being asked about f, we're going to answer this by knowing where is this positive and where is this negative. Okay, so we're retranslating number 1 into where is f prime greater than 0? And number 2, where is f prime less than 0? And now we can just look at the graph. Where is f prime greater than 0? Wherever it's above the x-axis. It's above the x-axis here, so that's -3 to -1. And it's also above the x-axis here, and that would be 1 to infinity. Same thing with number 2. Where is the original function decreasing? Well, we have the derivative, so we'll look where's the derivative less than 0. And the derivative is less than 0, the derivative is negative. Everywhere it's below the x-axis. All these questions are still wheres, everybody. So again, just answering by the x-coordinate, but these are intervals of x's that we're getting. So, just like we did before, where is the derivative less than 0? Well, it's under the x-axis here, so the original function is decreasing, -infinity to -3, all of this, and it would also be less than 0 here. That would be -1 to 1. The next two are a little bit tougher, because if we are going to figure out where f is concave up and where f is concave down, we're really going to need to know where f double prime is greater than 0, where f double prime is less than 0. But how am I going to know about f double prime? I only know about f prime. How do I go from f prime to f double prime? It's one more derivative. So this really pulls us. This is about as far as we can stretch it, everybody. What we're going to do to finish this, I am going to look at where f prime is increasing, decreasing, and that'll tell me where f double prime is greater than or less than 0. Do you see what I'm doing? I'm stretching this theorem. That now if the original function is f prime, the derivative of f prime would be f double prime. So one more time, everybody. I'm going to figure out where f double prime is greater than 0 by figuring out where f prime is increasing. Where is f double prime less than 0? Wherever f prime is decreasing. So now going to here, f prime, first thing I do, I start going up. So I'm going up at -infinity. I'm increasing, starting at -infinity, and I stop increasing here. That would be at -2. Then I start to go down, so I'm decreasing. So if f prime is decreasing, f double prime would be less than 0. So I'm decreasing from -2 until I get, maybe that's a tad bit off. I'm going to use 0. It might be right about here, but I'll just use 0. And then I start going up. So as I go up here, and that's it. The rest of this function is going up. F prime is going up, increasing from here forever. So that'll be 0 to infinity. F prime is increasing. F double prime is greater than 0. Whew. All that tells me f is concave up. F prime is decreasing, means f double prime is less than 0, tells me f is concave down. I could also do something slightly similar by giving you f double prime and just asking you about f is concave up, concave down, and that would be similar to what we did here.